Okay, so in the previous video, we have seen what are the maximum positive and negative shear forces. The second thing which we are going to learn next is maximum bending moment, okay, at any section C. So now you should understand that you have a set of point loads actually W1, W2, W3 and W4. So these loads will have definitely have a resultant acting somewhere depending on their magnitude and the distance with which they are spaced. So you have to find the resultant of that because that resultant when it acts on section C is going to give you a maximum bending moment. Okay, so that is our next case where we are going to calculate what is the maximum bending moment at C. So let us assume that R1 is the resultant. Okay, so let R1 be the resultant of loads on the left of section. Okay, so if the set of loads are to the left of section C, then let R1 be the resultant of loads on the left of section C, whereas R2 be the resultant of loads on the right of section C. So what I'm going to do is C or whatever the section which you are considering. So what I'm going to do is I'm going to position this set of loads in such a way that there are a few loads on the right of section C and there are a few loads on the left of section C. So I'm considering any case where there are a definite number of loads like this point loads, and to the left of section C let it be R1, the resultant is R1, and to the right of section C let it be R2. So let us also assume that the distance between this R1 and R2 or the resultants on left and right, let it be small d. And from the section C, the distance of R1, okay, at least one of them you have to, its distance should be with respect to C because C is the hero here. So let me consider it as X. Okay, now with this much data and also let us write down what are the values Z and L here. Let's mark it on the figure. So this is also there. Now we are interested in knowing what is the bending moment. So I'm going to draw the ILD for bending moment at section C, which is going to be a triangular variation. All you have to learn is how you have to keep the load so that your condition of maximum bending moment is satisfied. Now let this be YC, and since you are placing this like this, so I'm going to consider the resultant is having an ordinate Y1 here, and the resultant of the loads on the right hand side, that is R2, is having an ordinate Y2 here. Okay, if this much is understood, let us now move on to the derivation of condition. Okay, so all that I'm not going to write it here. The distance between R1 and R2 is D as shown in the figure, and R1 is at a distance of X from section C. Okay, now ordinate of ILD for moment at C is Y1, Y2, Y1 under R1, Y2 under R2, and maximum ordinate is YC. Okay, now what is moment at C? We can write moment at C as resultant in the left hand side into its ordinate plus resultant on the right hand side into its corresponding ordinate. So let us give this as equation 1. Now considering the similar triangle principles, so from similar triangles, you can write y1 by yc is equal to z minus x by z. So you know that this distance is nothing but x and this one is z. So y1 is nothing but z minus x. So we got this relation. From this, you can write y1 as z minus x by z into yc. Okay, let it be here. Then considering the other side, you can also write y2 by yc is equal to L minus Z. So this one is nothing but L minus Z. And what is this? This is L minus. So this small distance will be D minus X. Okay, because total is d, and this much is x, so this is d minus x. So this distance is L minus z minus d minus x. So just like how we did in the previous derivation. So L minus z minus d minus x divided by L minus z. Okay, from this y2 is equal to L minus z minus d minus x whole divided by L minus z into yc. Okay. Now let us substitute for y1 and y2 in equation 1 using these values which you have found. So in equation 1, when you substitute, you will get mc is equal to r1 into y1. So y1 you have got z minus x by z into yc plus r2 into L minus z minus d plus x. I've opened the bracket divided by L minus z into yc. Okay. Now for MC, what you want is MC to be maximum. So for MC to be maximum, what is the condition? dmc by dx, because you are positioning, you have to find the x or position of the loads so that you get a maximum bending moment, isn't it? So differentiating with respect to x, minus r1 into yc divided by z plus r2 into yc divided by L minus z into 1, because x is there, so into 1 should be equal to 0. From this, r1 into yc by z is equal to r2 yc by L minus z. Okay, so the yc's will get cancelled and you will get, finally the equation is r1 by z equal to r2 by L minus z. Now, doesn't it seem like a very nice equation, which it actually means that what is resultant is actually the average load. You can consider it as the average load. So this can be written in words as the average load on left hand side of the section should be same as average load on the RHS, because Z R1 by Z is nothing but average load on the LHS. R2 by L minus Z is the RHS part. So average load on RHS. This is the condition for maximum bending moment at a section. Okay. So I hope that is clear. Now there are a few things to know. That is, practically we hardly reach at such a condition. I mean, you cannot split a car and position it in such a way that you get an average load on left to be equal to average load on the right. So practically it is not possible. So what we do is, this is just an a calculation where, for example, when load W1 is to the left of the section, the average load on left side may be heavier. Okay, whereas when once it crosses the section, then you might find that the right hand side has become heavier. So you have to find out the load which that load which when it crosses the section C, that is causing imbalance, or until then, the left of section was heavier, but one load rolled over and the section right hand side has become heavier. So that load is taken as the critical load, and you will place that critical load on the section C and then draw the BMD for that, and calculate all the ordinates and calculate what is the value of maximum bending moment. This is all that is possible because you cannot actually achieve this particular condition in a practical case. So that is there. Also, due to the moving loads on a simply supported beam, the maximum moment at a section develops when load W1 is on the section where that particular load, which upon its rolling over to the next side has caused the right hand side to become more heavier. Then that load is, like I said, taken as a critical load. So that is only possible with the train of uh, moving load. So what you have to do is you have to find out that critical load which is causing that imbalance on the span. Okay, so that is about maximum bending moment. Now C part, which is next, you have to find absolute maximum shear forces. So positive and negative shear forces. Now, at any section, we have been learning, that is the ILD ordinate, influence line diagram ordinate for negative shear force is nothing but Z by L, and the same for positive shear force is nothing but L minus Z by L, isn't it? So at Z equal to 0, that is at A, point A, what can you write? ILD ordinate is nothing but 1, isn't it? So that means that 1 is a maximum. So what you have been learning till now, the same thing at Z equal to L, that is at B, your ILD ordinate is 1, which is again maximum. So you can understand that for negative shear force, it should be at A. This is corresponding to absolute maximum negative shear force, and this corresponds to absolute maximum positive shear force. Okay. So maximum shear force occurs when one of the loads is on support A. Once it starts moving from left to right, then the shear force decreases or negative shear force increases. And once the loads start crossing section C, there is an increase in the shear force, and it will contribute to an additional shear. Okay. So absolute maximum will be like this only. So any of the load should be on either of these supports, A or B. Only then you will get an absolute maximum shear force. But if you are trying to find the same for a section, then you have to check trials when each of the loads move over the section C. What is the change in shear, positive or negative?